Thank you so much. This is my first time visiting Singapore, and today and yesterday in meeting people and learning the exciting science that you do here. Thank you so much for your hospitality. So I'm from University of Science and Technology of China, and also the new Hefei National Laboratory. So these are my colleagues in Hefei. We are the laser laboratory for trace analysis and precision measurement. And so people ask me where Hefei is. It's west of Shanghai, west of Nanjing, but in that area. And these days, I was talking to David today, that it's quite easy to travel between Hefei and Singapore. There's a direct flight, 5 hours of flight, and there's no jet lag, no time difference. And so it's quite easy. So let's hope for more scientific exchanges, not just between professors, but also between our young people and the young people here. It'll be good for both of us. And our research is supported by the Chinese NSF, Ministry of Science and Technology, and also the Chinese Academy of Sciences. And so we're in the Anhui province. It's a beautiful area, lots of historical sites, and also beautiful sceneries. When you go back, please Google Yellow Mountains and look at the pictures when you Google that. And if you like that, please come visit us. So let me start with this. This is a recent Nature article summarizing 2 decades of deep ice cores from Antarctica. And here are the years when the ice cores are drilled, and also the depth in the vertical axis. And you can see over the time there are many ice cores are drilled. They're drilled to learn about the history of the Earth climate, right? So these ice cores are basically a natural record that kept, when it formed, it trapped ancient air, ancient water, and ancient dust particles in it. So it's like someone has been keeping a record for us for all these years. And now you can extract these ice and learn about the history of the Earth climate. And also by learning about the ice dynamics over the entire Antarctic ice cap, you can learn about the stability of this big ice cap. So how it would respond to climate change. So these are the important topics that glaciologists study. And over here at the end, there's a dot. So at the lowest part, there's a dot, and there's a year, seeming to indicate that this is the oldest ice people have discovered. That's not true. That's the oldest age that the glaciologists have determined using the known method. Okay, there are layer counting and also modeling, so, the ice flow modeling that can help the glaciologists determine the age, but they would require a continuous ice core. But as the ice gets deeper and deeper, the layers get thinner, and also the ice flow, so ice movement might have disturbed the order of the core. That in those cases, the relative methods no longer work. Okay, but they believe there are older ice beneath these points. And there are radioisotope dating methods that can help date the ice sample without knowing what's above and what's below. So these are the absolute dating method. Krypton-81 dating is this method. This isotope is radioactive with a half-life of 230,000 years, so 250,000 years. And it's continuously being produced in the atmosphere by cosmic rays. Okay, so cosmic rays coming down and neutron capture on the stable krypton isotope. And meanwhile, it continuously decays, so the two sides reach an equilibrium. Because it's a gas, it travels all around the world in the atmosphere and gets mixed really well. So there's a uniform distribution of Krypton-81 in Earth's atmosphere. Everywhere on Earth, if you grab a pocket of air, you measure its Krypton-81 isotopic abundance, you will get the same value. That's to be expected. And I think so far we have measured this air from all over the world, Antarctica, Greenland, US, China, and Pacific Ocean, and we indeed get the same value. So we call this value I naught. That's the isotopic abundance of krypton-81 in the atmosphere. Now, when snow gets packed into ice, it traps pockets of air bubbles inside the ice. So at this point, after this boundary, below this boundary, then the sample, this pocket is separated from the atmosphere. There's no more fresh krypton coming in. Meanwhile, the radioactive decay continues, right? So from then on, the isotopic abundance of krypton-81 decays exponentially according to this simple formula. So by measuring the krypton-81 abundance in the ice, you can determine the age of ice. That's a very simple principle. It's very straightforward. And this principle has certainly been applied very successfully on carbon-14. Like krypton-81, it's also produced in the atmosphere. And now, carbon itself is not a gas, but in the atmosphere, it quickly oxidizes into a stable form of gas, CO2. That's a very important step. Because of this step, then carbon-14 is also uniformly distributed in the atmosphere. And that makes radiocarbon dating so useful. So this was pointed out by Willard Libby at the University of Chicago in the 50s, and he received the Nobel Prize in chemistry for this work. And here is a decay curve of carbon-14, and so it's abundance versus age. It's an exponential decay curve, but it's plotted on a log plots. And I do that to show you that at the beginning, when the age is much less than the half-life, this part of the curve is kind of flat. So then it's not very sensitive to age. And on the old age part, this part then it's very, the curve has become steep, it's very sensitive, but there is a systematic effect that prevents people from applying radiocarbon dating. See, in the samples, during sampling or in the environment, there's always a little bit of modern carbon mixed in. That's unavoidable. And as a result, for example, if there's a 1% of modern carbon in it, then if you get the sample, you measure the carbon-14 abundance, you get 1%, which seems to suggest this sample is like 30,000 or 40,000 years old, okay? But it's actually not. This is due to a systematic effect. And there are lots of groundwater in the world. If you look at the record, they seem to suggest 30,000, 40,000 years of age. But nowadays, with krypton-81 dating, we find out it's much older, 300,000 years, even 1 million year old water in many places around the world. So the suitable age range for an isotope is limited, it surrounds its half-life, a few times below, a few times above. If you want date age beyond radiocarbon dating age, you want to use a different isotope with a different age, a different half-life, right? So in the Earth's atmosphere, fortunately, there are a number of radioactive gas isotopes. Their half-lives happen to fall into different orders of magnitude. As a result, the suitable age range links together from a few years all the way to 1.5 million years. Okay, so carbon-14 detection was solved a long time ago, but we are working on using the atom trap is to solve the detection challenge of krypton-85, argon-39, and krypton-81. So that's what we're doing. They are evenly distributed in the atmosphere. They are noble gas, so their transport process in the environment, in groundwater or in ice, is quite simple because they don't participate in chemical reactions. Okay, so they are ideal isotopes for dating and tracing. And this was realized already in the 1960s at the University of Bern by Hans Eschger and Ugo Lusling. They pointed out these are ideal dating isotopes. If someone solves its detection challenge, then they can be widely used in the earth sciences. The difficulty has always been the isotopic abundances are really low, into the -11, -13, And in this case, it's 10 to the minus 16. So the number of atoms are very small in a kilogram of water or ice. So that has been a challenge for many decades. Carbon-14 detection was also difficult. Its isotopic abundance is also at the 10 to the minus 12, but it was nicely solved by the accelerator mass spectrometry method in the 1960s. Okay, it's solved by this way. The problem with mass spectrometer identification is always the isobar contamination. For carbon-14, the isobar is nitrogen-14. It's abundant and it's everywhere in the sample. And also CH, a carbon-13 plus a hydrogen will give you a mass 14 particle, has a similar mass with carbon-14. So those are the background the mass spectrometry method always fight against. But in the 70s, people realized by raising the energy of the particle beam to a mega EV above, then you can separate carbon-14 clearly out of the background. This is due to several reasons. One, the particle identification can be based on not just for one hit on the detector, but actually you can measure its energy loss in a gaseous medium. So that's extra information. And if you use a tandem accelerator, so by starting with the negative ions and the stripping foil here, you can actually destroy all the molecular isobars. After stripping off a few electrons, the positive molecular ion will explode. It's called Coulomb explosion. So that removes all the molecular background. And finally, it was found accidentally that nitrogen-14 does not form negative ions. So simply, its electron affinity doesn't favor formation of negative ions. So as a result, if you start with a negative ion source, a beam of carbon-14, there's no isobar contamination from nitrogen at all. So that explains why there were simultaneous papers in Science magazine announcing the AMS method of carbon-14. It was a revolution. Before that, people had to detect carbon-14 by decay counting, which is very slow. If you want to date a famous painting before, you would have to burn the entire painting to get enough carbon-14 for the job, right? No longer. So with the AMS method, you can just take a little thread from the painting, and that's enough to date it. So that's how carbon-14 detection was solved. How about krypton? Krypton, unfortunately, it itself does not form negative ions. So that this regular AMS method does not apply. Well, that doesn't stop Walter Kuchera of the University of Vienna from trying using the positive ion source for the AMS. But then how do you separate krypton from its isobar, bromine 81? The method they used was for stripping. Basically, if you take away all the electrons from krypton, it can have a charge state of 36 plus, whereas bromine can at most be 35 plus. So then you can separate krypton cleanly out of the bromine background. That takes a lot of energy. So they used a 4 GeV energy from a Michigan State University cyclotron to achieve this. They actually did it, and they detected krypton 81. They performed the very first krypton 81 dating of groundwater back in 2000. And it was, of course, this used a very large facility. I think the accelerator occupied a building as large as this building. So it's unlikely to be an environmental analytical tool. And so, but this work really inspired me of trying to solve this problem using the atom trapping method. So the method we use is people here are quite familiar with is the laser trapping and cooling of neutral atoms. We no longer ionize the atom, just use neutral atoms. Krypton comes in through this pipe, and then we use laser beams to first cool, so Zeeman slowing and a magneto-optical trapping. And then people here all know that you can see a single atom in the trap, right? When I talk to geologists, they also find it fascinating that you can see a single atom clearly. but our colleagues here know this really well. There's another property that you may not have thought about because it doesn't occur to most of our atom trappers, but you would intuitively understand this. This moth has a super selectivity. When you trap rubidium-85, you never have to worry that it could be a different isotope or different element, right? And this is because the moth has super selectivity. It selects the isotope for you. And this is a very useful property. In fact, it's a unique property among all trace analysis methods. No other methods can claim that it's immune to all these other contaminations. Only moth can make such a claim, okay? And so what is our detection limit? Our detection limit is determined by our count rate, so how fast you can trap atoms, and then your patience, how long you're willing to wait. That's our detection limit. All other trace analysis methods are limited by some kind of background. So as the isotope ratio goes down and down, eventually there's some background, and then you cannot go below anymore, right? Not our atom trap trace analysis method. So there's no background at all. And this can be shown here. So as we scan the laser frequency, you can see the top part of the curve. That's the stable isotope krypton-83. Isotope ratio is 10%. And then the lower graph, you can see krypton-81, krypton-85. Its isotope ratio is 10 orders magnitude or 11 orders magnitude below the stable isotope, even though the stable isotope is only 100 megahertz away. But then you look at these small peaks on the side. The background is not just low, the background is zero, actually. So if you tune the laser frequency here, no matter how much krypton-83 you have on the side, that we don't register counts at all. That's the beauty of this smart method. Trace. Hey, but these are the great advantages of using a moth, but there was a flaw. Here is flaw. It's at the beginning. So when we first showed the method in 1999, the trapping efficiency was very low. So low that if we wanted to date ice, we would have to ask for 1,000 tons of ice. So this is completely unreasonable. And so it was only a proof of principle measurement at the time. Okay. Then a few years later, we developed the second generation of the setup. Now the efficiency is higher, and the sample requirement got down to 1 ton. Okay, and that's done by sample recirculation. So instead of pump the atoms away at the moth chamber, we actually use a turbo pump, and we put the output of the turbo pump back to the source. So krypton atoms never leave the chamber. It just goes around and around. That's how we boost the efficiency. You have to solve a few other problems, but that's solvable. So with 1 ton, we could start dating groundwater, because you can go to a well and you can let the water flow and strip the gas on the water. And then press the gas into a cylinder, bring the gas cylinder back. Okay, we don't have to bring 1 ton of water back. We just need to bring the gas cylinder back. So that's how we started doing groundwater dating. And so why do people want to know the age of the groundwater? And by the age, we mean how long this groundwater has been separated from the atmosphere. So over here, the groundwater age is 0, but as time goes, the groundwater gets older and older. What hydrologists really want to know is how the groundwater moves underground. Right? And the transport, the replenish rate, that's what they really want to know. With those data, then they can determine what's a sustainable, or at least a slow way of depleting this fossil water reservoir. The movement underneath the ground. So underneath the ground, the water it's not like a river. Water has to seep through sand and rocks, and the rate is very slow. It's on the order of a meter per year kind of rate. So it's very hard to determine with the direct observation. But if you have a network of wells and you pump water and you determine age of the groundwater at each locations, then by plotting out the map, you can figure out which way the water it flows and at what rate. Okay, so that's what the groundwater age helped hydrologists to determine. And so far, we have been collaborating with hydrologists and glaciologists and dating ice and water from all over the world. We haven't collaborated with scientists in Singapore. I think because here water resource is plentiful, so there's no need to use the groundwater resource over here. But this is a rare a rare occasion. In most parts of the world, groundwater is an important resource. Let me give you just a couple of examples. This work is done with Chicago geochemist Reika Yokochi. So I'm giving this in memory of Reika. She was a brilliant geochemist. She led this collaboration, and where we actually dated groundwaters at many sites in Israel. And from that, we found, after Reika's idea, that the groundwater in the underneath the desert Israel comes from only two moisture sources. So one was modern, and the other was 360,000 years ago. So there was a wet period back then, and then these two moisture sources mixed together to form all the groundwater in Israel. So Krypton 81 dating helps to reveal these characteristics. The other work we did was in collaboration with Dr. Ota in Japanese, the Central Research Institute for Electrical Power. There she studies sites for nuclear waste storage. If you want to pick a site for nuclear waste storage, then you want the place to have a very old groundwater. Therefore, the groundwater moves very slowly and it's isolated from the surrounding environment. So groundwater evaluation is the key for such evaluation. And here we sampled groundwater in the northern part of Japan. And we found the water under 700 meters, indeed old, so 200 to 300,000 years. So that's an important characteristic in the evaluation of these sites. That's another aspect of the Krypton 81 data. The International Atomic Energy Agency, very interested in this method. They've so far organized two collaborative projects already. From 2016 to 2023, we finished the first phase. Now we are in the second phase of this collaboration, where they picked 15 nations to collaborate with us and to use the long-lived radionuclides for dating very old groundwater. And in fact, just last month, we participated in a meeting on the application of atom trap trace analysis in water resource management, organized by IAEA. So coming back to dating ice, a ton is still too much for dating ice. So we spent some years, developed the third generation machine and reached 100 kilogram sample requirement. At that time, glaciologists said, well, that's enough. We can start doing ice dating. Okay, so this is our collaborator, Vas Petrenko from University of Rochester. He took a large vessel to Antarctica. So this is how you sample gas from ice. So you put the ice into the vessel and you have to cover it up. You have to vacuum seal, you pump away the air, and they melted ice in the field. And then when the ice is melted, the gas escapes, brings the gas back. So that's the whole process. Okay? With a few hundred kilograms, they could do it. But the ice was not deep ice, because it's too hard to have a few hundred kilograms of deep ice. This is rather shallow ice, only 20 meters deep. But even just 20 meters, we already found 100,000-year-old ice. because the entire Antarctic ice cap is a dynamic process in the ice cap. Old ice keeps pushing out, and they re-emerge at the surface near the edge of the ice caps. So if you go to the edge of the ice cap, you don't have to dig very deep to find old ice. That's our work about 10 years ago. And very recently, we finally reached this 1 kilogram goal we've been working towards for the past 2 decades. So now we are ready to date the deepest ice on Earth. This is our setup, and there are many people who are working with moths here, but over here, usually the moth is the beginning point, right? Your advisor tells you, go build a moth. Then we do science, right? But for us, the moth is the destination. We spend all of our effort trying to build the fastest and most efficient moth. So once the atom enters the moth, we have 100% detection efficiency, so that we've reached our goal. So this is what we have come up so far. It's very fast. For primary isotope, abundant isotope, our trap rate can go to 10 to the 12 to 10 to the 13th atoms per second. So that's very, very high. We need that in order to see this very rare isotope. And then also has to be very efficient because our number of atoms is really small. So in this case, for krypton 81, we reached about 20%. I think within a couple of years, we can reach 100%. So krypton gets leaked in over here. There's a little valve over here. It goes into the system and then gets transfers cooling, same as slower. And there's a moth. And here's a CCD camera that can see a single atom. Now, going from 100 kilograms down to 1 kilogram, there is a key technical breakthrough. I want to explain this to you. It's not at the trapping end. Rather, it's at the beginning, the source end. So we actually don't trap krypton atoms in the ground level because the noble gas, it's very hard to excite noble gas from ground level. Fortunately, noble gas atoms all have a metastable level. And when the noble gas atom has a closed shell, right? If you take an electron, you take the electron to the excited level. At the same time, you flip the spin. Then this excited electron is stuck over there. It cannot decay back because it has to decay and flip a spin. It's an M2 transition. The lifetime is very long. It's about 40 seconds. So for us, it's a metastable state. So if the atom is a metastable state, then we can use regular infrared laser, 811 nanometer light, to trap the atom. Okay? But how do we place the atoms into the metastable state? What we have been doing is what everybody has been doing, using a gas discharge. The discharge, the electron collide with the atoms and bump the atoms into the metastable state. The efficiency 10 to minus 3, that's actually quite respectable. The problem for us is that the discharge causes memory effect. Okay? So normally, a krypton atom does not stick to wall, right? It's a noble gas. So after we can do our analysis, after analysis, we open the valve, we can pump everything away, right? Not if you run a discharge. In the discharge, lots of atoms are ionized and they are accelerated into the wall and buried there, but only a few layers deep. Then they don't get pumped away. When you're ready to analyze second samples, you turn on the discharge again, then those discharge can drive the previous or even the previous sample back out. That causes cross-sample contamination. That memory effect has basically stopped us for the past decade of going down to very small samples. So we do wash the chamber between sample measurements. Usually we're putting some xenon gas, run a discharge, and see krypton coming out. We pump all these away. We do that. But even with a day, 2 days of washing, we still get a few nanoliter per hour of krypton coming out. And it's not exponential decay, it's a long, very long tail. We don't know where the krypton could be hiding in our system. So a few nanoliters, you say, well, why do you worry about a few nanoliters? When we had 100 kilograms of ice, we didn't have to worry about a few nanoliters. But 1 kilogram of ice contains only 100 nanoliters of krypton. And if this ice is old, its krypton 81 level is only 1% of the modern level, and we got a serious problem. It's a serious systematic effect. So this basically has prevented us from going down to 1 kilogram of ice. We solved the problem by avoiding the discharge at all, right? So we now use an all-optical method to produce the metastable krypton atom. So you can excite the krypton from the ground level up, and then you need 2 steps and 1 step down. Transfer the atom from ground level to metastable because the delta J equals to 2, and also there's a parity flip. So you need a minimum of 3 photons to do the transfer. The difficult part is the first excitation. It's at 124 nanometer, vacuum UV. We don't have that kind of laser to do the excitation. So we developed a resonant lamp. It's a lamp filled with krypton. Those are not glacial kryptons, it's just commercial krypton. You can strike a discharge on these commercial krypton gas. It emits light at the resonant frequency of krypton, and those light is used to excite the krypton atoms in the ice. That's the basic principle. Very difficult to do because the krypton gas not only emit light, but also absorb light. So there's a self-absorption going on. So it's a difficult development work. But in 2021, we finally succeeded in developing a lamp that's bright enough, and it's resonant, and it's durable enough. It lasts long enough. Now, the lifetime nowadays is 100 hours. And so every 100 hours, we have to switch the front window, which is magnesium fluoride. But that's okay. We can manage to do that. With this development, our outgassing rate is now down to 20 picoliters per hour, and the memory effect is solved. Okay, that's the key. And the heroes behind this development is our former graduate student Jay Wan and the former postdoc Florian Ritterbusch. They tried lots of different lamp design, but it was actually during the COVID era they finally found a design that works. So this is the performance specs of our 1 kilogram machine. The vertical axis is krypton uncertainty, age uncertainty, and then the horizontal axis is age itself. Certainly with more samples, we can do a better measurement, more precise measurement. But also has to do with age. If the age is too young or too old, then our precision goes down. Right? So that's why for each isotope, there's only a limited suitable age dating range. And so we talk to glaciologists, and often I get a question, well, you've been improving for the past 20 years. If we wait another 3 years, will you get better? So we don't have to give you 1 kilogram, maybe only 100 grams of ice is enough. Those deep ice is very precious. Usually the glaciology group, when they apply for ice sample, they get grams. So gram is a standard unit in ice allocation. So when we ask for 1 kilogram, it's a lot. So we explain to them there is a fundamental limit. So when ice formed, the number of 81 atoms in the piece of ice, it's actually a Poisson distribution in it. And the radioactive decay also has a Poisson distribution in it, right? So when we get a piece of ice, the number of krypton 81 in it has this statistical error that has nothing to do with our measurement. Even if we can count every atom perfectly, this error remains. So that's the fundamental error for krypton 81 dating. And that's what this dashed line is. we're getting very close to this fundamental limit. I think in a couple of years, we will reach this limit. So this is the process. Basically, you melt the ice and get the gas out. Nowadays, we no longer need large pressurized vessels. We just need a gas bag. And this bag gets mailed to Hefei. And then we purify the gas to get the krypton. Krypton in air is about 1 ppm. So from 1 liter of air, we get 1 microliter of krypton, and then send the krypton into the trap system and count krypton. So that's how we do the entire process. So we get these bags from all over the world. It's always fun to watch the delivery person coming in with a large box from Europe. Obviously, it's an important thing, yet it weighs nothing. I was curious, we get shipping. We're shipping air, but it's the air of 1 million years ago. And so we have dated the basal ice in Greenland. We are part of the European and American collaboration with a very interesting title for the project. The title is, when was Greenland actually green? When was it free of ice? Okay. And the goal is to find the oldest ice in Greenland. And so when we applied for, so where do you get these ice? You actually don't have to go to Greenland or Antarctica to get old ice. You go to Europe and America, various places where they keep the old ice. So when we applied to the US National Science Foundation for ice, the panel has an opinion that said, well, so they say this was the established age versus depth curve for the Greenland ice core. It went all the way down to 2,700 meters depth, and age went up to 100,000 years. Below that was not known. So the panel said, well, it could be a little bit above, so 100,000 years, could be 400,000 years, it could be 1 million years. We don't know. We have recently measured 3 samples, and this is the results we have. And if we expand this result, this is 3 samples we have measured. So from 500,000 years to 700,000 years. So that's the age of the deep Greenland ice. The age versus depth order is well preserved. It could mean that the deeper the ice, the older it is. There's another explanation our glaciologists are working on right now, that it could also be due to ice mixing. So there's a very old component, there's a young component, and then as ice moves, they mix the old with the young. And so this may have also caused this depth versus age relationship. We don't know which model is correct. So this is the ice samples. The ice was supplied by our Princeton glaciology team, Sarah Shackleton, Michael Bender, and John Higgins. And you can see this ice. And the basal ice is quite dirty. Looks like this, but it only has about 1% of dirt in the ice. 99% is still good ice. So we have 3 chunks, and for each sample, we used about 1.5 kilograms of ice. And this is a result. And what's clear is that the central Greenland ice sheet has survived marine isotope stage 11. This was a long interglacial period about 400,000 years ago. So that was the question, and the Krypton 81 data helps to review. In addition to dating the oldest ice, people could actually date the bedrock underneath the ice. From that, you can also answer the question, when was it actually green, right? So because when there's an ice cap cover, then the bedrock was not bombarded by cosmic rays. Okay? But when ice cap retrieved, then the bedrock started being bombarded by cosmic rays. Then radioactive isotopes start to grow inside the bedrock. So that's another way of dating the Greenland ice cap. It's called exposure dating. And in fact, before us, there was this 2016 Nature article that dated the bedrock of Greenland ice cap, and using beryllium-10 and aluminum-26 isotopes. And they couldn't pin down which scenario, but they proposed 3 scenarios. Scenario number 1, number 2, and number 3. And here the bluish part means ice, and the reddish part means ice-free. There are 3 scenarios, and our data clearly support the scenario number 1, and ruled out number 2 and number 3. These scenarios were proposed with the oxygen-18 data in the ocean sediments. So if the ice cap forms on land, then this water has to be taken from the oceans. Okay? But as ocean water evaporizes, the lighter oxygen isotope leaves first, leaving behind heavier isotope behind. So by measuring the oxygen-18 isotope abundance in the sediments, you can figure out whether the water is leaving the ocean or staying in the oceans. So the when this number goes up here, and then that means warm interglacial period, and it goes down, that means cold glacial period. So these scenarios will correspond to this interglacial and glacial period modeling. There is a big mystery in the earth science. If you look at the interglacial glacier change, it used to be faster. So it was called the 41 kiloyear world. Every 41,000 years, there's interglacial glacier oscillations. But nowadays, in more recent years, it became 100,000 years. Why is that? We actually don't know. There are many theories, many models. Okay, and in between, switch between the 41 to 100 is called the mid-Pleistocene transition. Okay, and what we found is that in Greenland changed from no ice to ice also in the mid-Pleistocene transition. We know these 2 things happened in the same period. We don't know whether there's a causal relationship between the 2, whether one caused the other, that's unknown. So this is ongoing research. Okay, so another point is that how come beryllium-10 and aluminum-26 can support multiple scenarios? This is because these 2 isotopes, very high, have a long half-life. So 1.5 million years, 700,000 years. So it's like a low-pass filter. So these rapid changes would not affect beryllium-10 and aluminum-26. It would be very, very nice, geologists say, to have an isotope of shorter half-life to do the exposure dating also. And so this is a motivation to develop calcium-41 with a half-life of only 99,000 years. And so this we did very recently. In fact, calcium-41 was talked about back in 1979. There was a Nature article with the title, Possible Use of Calcium-41 for Radioactive Dating. So it was discussed then. But again, because the isotope ratio is so low, the AMS couldn't solve the problem over the past few decades. Okay? But now, using the atom trap analysis method, we have solved this, this problem, detecting calcium-41 in the environment. At 8 times 10 to the minus 15, our count rate is 48 per hour. And the lowest we have analyzed so far is 10 to the minus 18. This is not the detection limit of our system. This is simply the lowest sample we have encountered. If you buy calcium, metallic calcium from chemical companies, the ratio is actually high. It's in the 10 to the minus 17 range. Okay. So since realizing this method a year ago, we've been measuring rocks, bones, teeth, sediments, and anything we can. There are a lot of calcium-rich samples in this world. And so this was the team who made this discovery. I should especially point out Hongyan Xia, who is here as a CQT postdoctoral fellow. We're very proud of him. And he won this year's Chinese Academy of Sciences Outstanding Dissertation Award. And so we're sending our outstanding students here. We hope some of the CQT students will go join our USTC effort as well. So we'll have the talent to flow back and forth. Physics Today had an article last year said that trapped atom analysis pushes calcium-41 onto the radiometric dating scene. So the detection problem is solved. Whether it can be used for dating, we don't know yet. So we're exploring. And one scheme that was also proposed a long time ago in the 80s by our senior colleague I know, Walter Henning. This was his hand drawing. He said, well, this could be used for dating bones. And on the surface, calcium-41 is produced by neutron capture on the topsoil. And so this ancient person could be digesting plants and then getting the calcium-41 from the topsoils. Now, if the person dies and lies down here, then it doesn't work because the calcium-41 will continue to be produced by cosmic rays. But if the person goes into a cave and dies there, then calcium-41 production stops. Then the radioactivity happens. So this would be a scheme for burial dating using calcium-41. So we are working on that. But one natural place we think this would work really well is in the oceans. Then fish swims around, gets calcium-41 from the water, and the calcium-41 is mixed really uniformly in the oceans, so gets a worldwide uniform value. Just like atmosphere mixes krypton-81 and carbon-14, ocean could mix calcium-41. And when the coral reef and fish dies, then it goes to the bottom of the ocean. And naturally, it's shielded from a further cosmic ray production. So this is the perfect place to first establish burial dating using calcium-41. The first task for us to do is to see whether calcium-41 is uniformly distributed in the ocean. So we've been doing this for the past year. Our measurement is very slow, only 2 samples per week when it's working properly, okay? So this is the data we have so far, okay? And we're very glad to see that in the deep ocean, 2,000 meters and below, it is indeed uniformly distributed. The global deep ocean value is 7 times 10 to the minus 17. That's great news for us. Calcium-41 burial dating will work for the ocean sediments. What's strange, above 1,000 meters, calcium-41 varies quite a lot, from 1 to 4 times 10 to the minus 16. What could cause this difference? We think this is due to nuclear testing, 60s and 70s. The hydrogen bomb that was set off in the Bikini Island basically activated the soil on the island, and those calcium-41, artificially produced calcium-41, gets washed around and goes around the ocean, and that causes this big variation on the surface. But because it will take hundreds of years for the surface water to go down, therefore the deep ocean has not been affected yet. So that's what we have found so far. So that these are the things we're exploring. Basically, I'm here at the Center of Quantum Technology. This is an example of quantum science and technology being applied to different branches of earth sciences. Thank you very much.